In this video, I'll walk you through the steps you need to take to perform nodal analysis in a circuit diagram so that you can come up with node voltages that will allow you to figure out other voltages and also the branch currents throughout a circuit. I'll also walk you through different cases and scenarios, so by the end of the video, you should be able to apply nodal analysis to any circuit diagram that you see. So let me get started with that. So here's a circuit diagram, and the first thing you need to do in order to perform nodal analysis is you need to identify what we call essential nodes. So just as a quick reminder, a node is just simply a point that connects two elements. While an essential node is also a point where you connect several elements, but it also connects more than two elements. So we call it a node if it only connects two elements, and we call it an essential node if it connects two or, well, more than two, three or more. Like you can also have like a fourth element that connects to that particular essential node. So your first step in nodal analysis is to identify the essential nodes on the circuit diagram. So in here, I believe this is an essential node in here, so I'm going to highlight it. This is an essential node, I'm going to highlight it, and the bottom wire is as a whole is an essential node. I'll just highlight it. So this one here is the first node I identified because it connects three elements, the 5 ohms, the 4 ohms, and the 14 amps current source. So the second node that we identified in here is that it connects also three elements, the 5 ohms, the other 5 ohm, and the 7 amps. So that's why it's an essential node. And the bottom one in here is just simply connects 1, 2, 3, and 4. It connects 4 elements, so that's why it's also an essential node. So the first step is to identify these essential nodes. So the second step is that you need to choose one of these nodes as a reference node. And frankly speaking, the choice of which one is the reference node or the ground node is arbitrary. You can choose any of them and nodal analysis will still work. However, your choice will make it either a little bit easier or a little bit harder to compute the equations or solve the equations. So with experience in solving multiple diagrams or multiple circuits, you'll be able to identify that maybe this should be my nodal voltage because of so and so. But typically a good starting point, if you're not sure yet, is to figure out, well, which one of these essential nodes is connected to the most number of elements. And in our cases, it's actually the one at the bottom because it's connected to 1, 2, 3, 4 elements. And the other ones are just connected to 3 elements. So I'll choose it as my reference point. So that's the second step. So the first step is identify the essential nodes. And then the second step is choose one of them to be a reference node. A good starting point is one that is connected to many other elements. Okay, so what's next? Well, next is, we need to write certain equations, and the number of equations that we need to write depends on the number of nodes left. So in our cases, and let me formalize it in here. So the number of essential nodes that we identify is here is 3. So what we need is ne minus 1, which is in our case 3 minus 1 equals 2 equations in order for us to perform nodal analysis. So with just 2 equations, we'll be able to solve this particular circuit. And in these 2 equations, what it will do, it will give me a couple of voltages. The first voltage, I'm going to assume that this is point A, so that will be VA. And this one here will be VB. That's a plus, and that's, of course, the minus is in here, or you can identify it's in here. Okay, so that's what it does. It gives me VA and a VB, or actually we're going to write it so that we can compute VA and VB. And if I know VA and VB, those are the node voltages. So sometimes nodal analysis is called node voltage analysis, because if I know the node voltages of these 2 points, I'll be able to figure out all the other voltages and the currents in the circuit. All right, so let me now focus on point A and write the nodal analysis equations for that particular node. So here, I'm going to just say that this is a node A, okay? So, and I will redraw it in here just because it'll make my life a little bit easier. So that's VA, and that's basically another resistor in here, and that resistor goes in here. And I have here, I'm going to just do this as VB, this is VA, and I have this is a 5 ohms, and I have here, and I will just say this is 4 ohms, and this is basically my reference point. That's what I'll say. Okay, all right, so I just redrew this part of the circuit only, just this part in here, and because I just want you, or I want to focus on this. So the way that nodal analysis works, or node voltage works, is by applying KCL at these nodes. So I'm going to say that what we do is we apply KCL at these essential nodes. All right, so the first thing you need to do is you need to identify or assume where the currents are leaving or coming in or out of this essential node. And frankly speaking, throughout the years, I found it the most or easiest is to assume that all the currents are either leaving or coming into the node. Frankly speaking, I usually use leaving. So I will assume that this one here is my I1, okay, and I'll assume that this one here is my I2, and I'll assume that this one here is I3. And this is just when I'm writing these KCL equations. I'm not assuming that these are the currents going through the circuit. I'm just assuming them for the purpose of focusing on writing an equation for nodal analysis. All right, so identify these currents. So KCL tells me simply the sum of these currents should be equal to 0. And of course, because all the currents are leaving, and if I assume that leaving is positive, so it's just simply I1 plus I2 plus I3 is just simply 0. Okay, so that's pretty much nodal analysis. So what we need to do is we need to convert these currents into voltages, or in terms of voltages, in terms of the VA and the VB. My ultimate goal is to come up with two equations that only have VA and VB and solve them. That's my ultimate goal in nodal analysis, because that's what I'm looking for, just VA and VB. Okay, so well, let's get started in here. Well, let's see what can we do about VA. Well, VA, it's coming from here. So if you think about it, it's the opposite of that 14 amps. So I technically know what I1, it is just negative 14 amps. It just, because it's the opposite of a current, I know that it's coming in here. But anyway, again, because I'm writing nodal analysis equation for this particular point, I assume that it's leaving, but that regardless of what's happening in the circuit. So I'll just, because I know that it's coming into the circuit and I assume that it's the opposite, I'll just put negative 14. All right, what about I2? Well, where's I2? Well, I2 is just here. Well, I2 is just simply, this is plus, this is minus, this is actually VA, and based on Ohm's law, I can just simply say that this is plus VA divided by 4 ohms. Okay, so what about I3? Well, I3 is the voltage difference. Well, it's I3 is the one going through this particular resistor. So again, based on Ohm's law, I'll have to figure out the voltage divided by the 5 ohms. But which voltage? Well, it is the voltage between these two places in here on the resistor. So if I assume that this is VA and this is VB, well, the voltage drop across that 5 ohm is just simply VA minus VB, and that equals 0. And as it turns out, that this is actually our first nodal analysis equation in here. So it includes VA, it includes VB, and that's about it. And that's what I'm after. I'm after equations that include VA and VB. Of course, I need another one, which we'll get from the VB in here. So I have to clean this equation a little bit so that I basically sum up or combine VAs together and combines VB together so that I have just a simpler equation. And that will be in the following. So we can just say that 1 over 4 plus 1 over 5 VA. This is coming from these two in here. So I have the 1 over 4 and 1 over 5 for the VA. And then, of course, I have minus 1 over 5 VB. And that should be equal to 14. And then 1 over 5 plus 1 over 4 is just simply 9 divided by 20. VA minus 1 over 5 VB. And that is 14. And that's equation 1. So let me just highlight this one here. So this is the first nodal analysis equation. Okay, so we're going to just do this here and we're going to call it equation 1. So what we need to do now is we need to go to the second node in here, this particular node, and we have to do pretty much the same thing. I'll redraw it down just so that we can see it and we can focus on it. So here, I zoom down a little bit so that I don't have to scroll up and down. Okay, so we do that, and first we're going to do this here. This is the 5 ohms in here. This is VA, this is 5 ohms, and this is VB that I'm after. And then this one here is another 5 ohms, and it's actually connected to the reference point. And then this one here is just that. So again, what I did is I just focused on this particular part of the circuit now. So I'll highlight the current again, similar to the first case. So now I am doing this now at point B. So this is at essential node B. So what I will do is I'll assume also that all the currents are leaving that. Here is I, and here's another I, and here's another I. I can just call this I4, and this one, for example, an I5, and this one here is I6. Okay, and I'd write KCL at this particular essential node. So KCL at this particular essential node is the same as the first one. I assumed all of them leaving the node just so that it's simpler on me. So I can just say I4 plus I5 plus I6 is simply equal to 0. And now I'll have to figure out what the different I's are. So what is I4? Well, I4 is the current going through the 5 ohm from VB to VA. So it is here, we write VB minus VA divided by 5. Well, just as a quick note, that this I4 is the complete opposite, or basically it's the same as I3, but it's moving in the opposite direction. So in I3, take a look in here, you'll see that it's VA minus VB. Well, now with the I4, it's VB minus VA. So I'm assuming that the B is higher than the A in this particular case, because I'm assuming that is leaving the node. Typically, nodal analysis, that's what we do. At each node, we write its own Ohm's law and its own equations. Okay, what about I5? Well, simply I5 is just a simple implementation of Ohm's law. It's VB divided by 5. What about I6? Well, I6 is, well, it's here. It's leaving the VB is, well, I know what it is. It's just 7 amps. So all I have to do is just say that's plus 7. And that's the second equation that we got from nodal analysis. What I need to do is I need to clean it up a little bit. And I just say it's negative 1 divided by 5 VA plus, I believe it's 1 divided by 5 plus 1 divided by 5 VB equals negative 7, and clean it up a little bit, negative 1 divided by 5 plus 2 divided by 5, well, this here is a VB, or VA, and this is VB equals negative 7, and now this here is the second equation. Okay, so let me highlight that. All right, so now I have two equations, two unknowns. So all I have to do is just solve this one and this two, and here I just need to solve them, and I'll be able to figure out what VA and VB is. Just simple two equations, two unknowns. You should end up with the solution that VA is just simply 30 volts, and then VB is just simply negative 2.5 volts. Now, knowing this, I go back to the circuit. So in here, I will say that this one here is 30 volts, and now this one here is negative 2.5 volts. All right, now I can figure out everything I want about the circuit. You want this voltage drop across the 5 ohm. All you have to do is just tell me it's 30 minus 2.5, so it's 32.5 volts. You want the current going through this particular element. Simple. Okay, what you do is it's actually VB. Well, I know that VB here is in the opposite, so VB well, you want the current. The current is just simply, let me just write it in here. The current, let's call it IB, going that way. Okay, just simply VB, which is negative 2.5 divided by 5, and that will be the current going downwards in here in the 5 ohms. And you can compute any current and any voltage in this particular circuit. So this is how, in reality, or in simplest term, how you apply nodal analysis in a circuit like this.